This one, this method, so it is faster from a calculation point of view. It doesn't show you the resultant quite as visually, so that's the downside. But let's go ahead and start this just to be back to where we were before, because that wasn't supposed to be there. We had this question as posed to us, and it said to what is the resultant of F1 and F2, and at what angle does it act with respect to the x-axis shown? And you can see the x-axis here pointing to the right. And the angles, and the vectors were 80 pounds acting at 20 degrees left of vertical, and F2 of 200 pounds acting 40 degrees to the right of vertical. So if we're doing this the orthogonal vector way, what we need to do is find the components, the x and y components of F1 and F2. And all we got to do is we know that the resultant's x component is equal to the summation of the x components of F1 and F2, and the same for the y. So then you can add them together, you get the overall, if you add the x components together, you get the x component of the resultant. You add the y's together, and you get the y component of the resultant. And that then you can do square root of the sum of the squares and get the resultant value, and then you can also use a tangent relationship or some orthogonal trig relationship to find the angle. So let's do it. A helpful thing to do probably here would be to draw the components for each one. So I'm going to have an x component, and I like to draw my components different than my vectors themselves. As we go on throughout the semester, you'll see that it can be helpful once you start having a lot of vectors. So it's kind of pointless now, maybe, but in the future you'll see that there's a reason to it. So I like to draw my components as like dashed lines just to differentiate them. You can do whatever you want. So I'm going to have the x component vector come up like something like this. And that's like F2 sub x, or whatever you want to call it. So F2x, and then my F2y would be like right here, right? And then my F1x would be something like that, I guess. F1x, whoop, I forgot to do my F2y. All right, and then I've got my F1y. All right, cool. So we just need to find our components. Let's do our x components first. So our x components. Now, I know that many of you have taken math, years and years and years of math, and you're sick to death of it, but you also, you were taught certain rules, and, they like to talk in math about it, your x direction and your y direction, and then they have some angle theta, which swings counterclockwise from the positive x. And that's great. I mean, that's actually excellent. We don't always have that angle. If you wanted to draw theta for each one of these on here, think about it. For F2, it would look something like that. And it would be like 270 plus 40, so 310 degrees. And that's fine. You could do that if you wish, but really a lot of times when you're up, say you're underneath the ceiling looking up at this eye bolt, you would not think to swing an angle all the way up through the ceiling and back down. That's really tedious. So this 40 degrees and this 20 degrees here, they're very realistic, very tangible angles that you could see, in this problem. The thing you just have to get into your head is that you have to look at the trig for the angle as presented to you. Meaning, don't just always say that the x component is the cosine of the angle. That is not the way it is. Here, if you look, the x component of F2 is actually not going to be the cosine of 40 degrees. It's going to be the sine of 40 degrees, because it isn't the same thing as this value right here, right? Which is opposite over hypotenuse, right? Remember, right? Very helpful. You're going to be doing a lot of trig with that, so get very fluent with, is it sine, is it cosine? Be able to work with it on the fly. That's going to get you extremely far in this class if you can do that. All right, so our x components. We'll say F1 x, and that's going to equal 80 pounds times the sine of 20 degrees. And that is acting, note that's acting to the left, so therefore that's going to be negative, right? It's going to equal, let's just say it's going to equal a negative 27.36, and that's going to be acting to the left, so 27.36 pounds. All right, F2, whoops, let's keep our color coding, it'll make it easier for us. F2x is equal to 200 pounds times the sine of 40 degrees. And that's acting to the right, so our signs can stay as they were, and that's going to equal 128.56 pounds. And so those are our x components, so we add them together. We are going to have, when I say add, you got to use the signs as presented, so a negative 27.36 plus the 128.56 is equal to 101.2. So this you could say is like, well, we were calling that R before, weren't we? Let's say it's R sub x. So that's the x component of the resultant, 101.2 pounds. That's the x component of the resultant. And now let's do our y components. And a lot of times, while I'm writing this, a lot of times I write F sub R for my force resultant. I'm doing R here because that's what I did on the last example, but you'll see it. I'll kind of do whatever. The main thing is if you're clear in your diagram, it's going to be clear to anybody that's looking at your calcs. So my y components, now I'm going to use the cosines of the angles because they're both, again, angles to the vertical, and so you can see that the cosine is the adjacent over the hypotenuse, so we want to find those. So F1y is going to be equal to 80 pounds times the cosine of 20 now degree. And that's going to be acting down. See right there, it's acting down, so that's going to be negative. And that is equal to 75.18 pounds. And then F2y is equal to 200 pounds times the cosine of 40 degrees. It's acting down, so it's also going to be negative. And that's going to be equal to minus 153.21 pounds, which is then going to give us our, if I add those up, it's going to be my R sub y, and that is going to be minus 228.4 pounds, which is, that's 228.4 pounds, acting down. Okay, so to finish this up then, if we were to draw this, and if I draw it on here, I'm going to say that I've got an x of 101.2, and which is probably going to be something like this, right? So 101.2 pounds in the positive x, and then 228.4, right? 228.4 pounds. So if I did my resultant of that, you could see it would be something along those lines, right? And so there is my r's. It's going to be the square root of the sum of the squares. So I could say that r here equals the square root of 101.2 pounds squared plus technically a negative 228.4, but that negative is going to square itself out of existence. Square root of the sum of the squares is going to give me equal to 249.8 pounds, which I believe is exactly what we had in the previous example. So yay for us. and the angle at which it acts. The angle at which it acts, I did a kind of a bad job of drawing that R here. Maybe to draw it a little better, it's really like down here, isn't it, if I drew it graphically. Okay, so there's my vector R. And if you think about it, we want to find this angle right here. And we didn't really give it a name last time because we added a couple of vectors together. If you recall, we found a little angle alpha there. We're not doing it that way this time. This time we're going to find this outright. So let's give this a name. I'll just call it phi. You call it theta. You call it whatever you want. Call it Bob. And if I want that angle phi, I could do it by looking, and maybe we draw this a little bit more clearly over here. If that's my resultant and this is my x component, and then I have a y component, I can move to that side. There's phi, right? So all I did was take the y component, put it over there on the right hand side. It's going to be, this is ry and this is rx. Phi is going to be the arc tangent of ry over rx. So phi is going to equal arc tangent or inverse tangent of ry over rx. And I'm going to, since I'm looking for the angle as it's drawn, as I drew it over here, let me draw that phi a little bit better. Note I'm already pointing ry down, so I've already defined that phi is going to be acting, clockwise from the x-axis. So I'm going to put the positive value in there for ry that you would see there, because if you notice I drew it with the vector pointing down. So this is going to be the inverse tangent of 228.4 pounds over 101.2 pounds. And so that gives me an angle of 66.1 degrees, which is exactly what we got before, just through a very different method. If you had put the minus 228.4 pounds in versus the versus the positive value, you would have gotten negative 66.1 degrees. And if you think about it, without getting too poetic here, if I said that ry was positive up, right, then I would have had this value. Here would have been my ry, and there's my r, and this is rx, and this is phi. Well, I would have actually needed to plug in the negative of that right there, and theta and phi would have then been a negative number. I prefer to draw it graphically on here, find phi as it's showing itself to me, and then decipher how that fits into the overall problem statement. So here is the example using component addition of vectors.